In this video lecture, we will go through Nernst equation and then we will see its derivation, how to derive Nernst equation. Right? So Nernst equation simply is used to calculate electrode potential when the conditions are non-standard. When we say the conditions are non-standard, we mean temperature is not equal to 25 degrees Celsius, right? Pressure is not equal to 1 bar, and concentration of ions in the half cells is not equal to 1 molar, right? Like we have been doing in previous lectures when we calculated single electrode potential, electrode potentials, and when we studied electrochemical series, we considered that the reaction conditions are standard conditions, right? So now what if the reaction conditions are not standard? If we change the concentration of ions in the half cells, in these two half cells, if we change the concentration of zinc ions or the copper ions, how will it affect the electrode potential? Or if I change the temperature of the solution, then how will it affect the electrode potential? All this can be calculated from Nernst equation, right? So we'll just quickly write the Nernst equation, then we'll derive the same. E is equals to E0 2.303 upon RT. R is your universal gas constant. I'm sorry, it goes here. RT is your universal, R is your universal gas constant, T is your temperature, N is the number of electrons exchanged in the redox reaction of electrochemical cell. Like this is an electrochemical cell. In this reaction of electrochemical cell, 2 electrons are exchanged. That means zinc transferred 2 electrons, it lost 2 electrons that are gained by copper ions in the reduction half cell. So here the value of N would be 2, and F is your Faraday constant, or F is the charge on 1 mole of electrons, which is 96,500, right? This is charge on 1 mole of electrons, which is 96,500 coulombs, right? Then log of ion concentration, right? So here this equation, if you look at this equation, it relates electrode potential with the ion concentration, right, and with the temperature, right? These two things can be varied, right? So, and the value of E naught can be taken from the electrochemical series that we have studied before this lecture, right? And we know that in electrochemical series we have standard reduction potentials, right, which are in the decreasing order in that series, and the value of standard reduction potential is measured by coupling given electrode with the hydrogen electrode, right? And both the cells, right, since we said that single electrode potential cannot be measured, right, so we coupled the electrode, right, whose reduction potential needs to be calculated with the hydrogen electrode, right? So we calculated the electrode potential of the given electrode, right, with respect to hydrogen electrode, right? So it's standard hydrogen electrode, right? So reaction conditions are maintained at standard states, right? So the value of E0 can be calculated or can be seen from electrochemical series, right? So it tells us how E varies with concentration of ions and temperature, right? This is what Nernst equation tells us: concentration of ions and temperature. Now if you just recall, we have done in electrode potential, when we studied electrode potential, we mentioned that factors on which the electrode potential depends, right? And how electrode potential develops. These zinc ions, zinc will oxidize as per this reaction. It will form zinc ions. Zinc ions will enter the solution, right? It will form a positive layer of ions, right? These electrons will stick to the electrode and it will form negative ions. This is known as electrical double layer. Now since we have charge separation, so a potential difference is created. Same is in the reduction half cell. So this electrode potential, right, electrode potential depends on two things. First is your concentration of ions, right, due to which this positive layer is created, right? And the second is your temperature, right? So electrode potential depends on, first is your concentration of ions, and if you remember, we have discussed that reduction potential is directly proportional to concentration of ions and oxidation potential is inversely proportional to concentration of ions, right? So I'll just write it over here. Oxidation potential is inversely proportional to concentration of ions, right? When the concentration of ions was less, concentration of zinc ions was less in the electrolytic solution, then more and more zinc is getting oxidized, right? So in the beginning, the oxidation potential was increasing since zinc has higher tendency to get oxidized, right? So when the concentration of ions has increased in the solution, right, concentration of zinc ions has increased in the solution, some of the zinc ions, what they did, when the concentration of ions is high, some of the zinc ions gained electrons from this rod. They collided with the rod and they gained electrons, right, to form neutral zinc atom. So slowly this will increase. As the number of ions will increase, this reduction will increase. That is, the reduction potential will increase, right? So this is happening, this reaction is occurring when the concentration of ions is increasing. So we say reduction potential is directly proportional to concentration of ions, right? Remember these two things. And the second factor was reduction potential depends on the temperature, right? Now just do one thing, just try to relate the factors on which electrode potential depends, right, concentration of ions and temperature, with the Nernst equation, right? So you will find we are aware of factors that are there in the Nernst equation, right, or the quantities that are there in the Nernst equation that tells us how electrode potential varies with this concentration of ions and temperature. So in short, we can say that if we take a qualitative if we take the quantitative relation of the factors on which electrode potential depends, right, this is the quantitative relationship of the factors on which the electrode potential depends, that is the concentration of ions and the temperature, right? So this equation, Nernst equation, is quantitative relation between electrode potential and factors on which E, that is electrode potential, depends, right? And this equation was first formulated by Nernst Walter, right, who is a German physical chemist. So the name of the equation is in honor of this German physical chemist Nernst Walter, who first formulated it, right? So this is it. So this is the Nernst equation that we will go ahead and use in many numericals. We get many numericals on Nernst equation, right? So just remember, it's a quantitative relationship of the factors on which electrode potential depends.